as we are full on into the day 3 of the Qiskit Fall Fest 2025 here at RGUKT Srikakulam. It's been an extraordinary journey so far, a confluence of curiosity, intellect, and innovation. And today, we continue that voyage into one of the most fascinating frontiers of our time, quantum machine learning. Today, we are deeply honored to have with us, joining us virtually from Spain, a scholar, a visionary, and one of Europe's leading voices in quantum computing, Dr. Elias Fernandez Combarro Alvarez. Dr. Fernandez Combarro is a full professor in computer science and artificial intelligence at the University of Oviedo, Spain. His academic journey has been nothing short of exceptional, a national award winning mathematician and computer scientist who secured both the Premier Premio Nacional and the Segundo Premio Nacional de Fin de Correro, recognizing him among the very best in his nation. With a PhD in mathematics and a profound background in computability theory, machine learning, and quantum optimization, he has pioneered research that bridges classical intelligence with the quantum paradigm. He currently serves as Spain's representative on the advisory board of the CERN Quantum Technology Initiative and also contributes to She Quantum and Q Spain, shaping the landscape of quantum education and innovation across Europe. His contributions have illuminated new paths in quantum algorithms, optimization problems, and its applications, and quantum machine learning, inspiring both researchers and learners worldwide. Today, he will take us on a journey through the fascinating world of quantum machine learning and its applications, exploring how quantum principles are transforming the way we perceive computation, pattern recognition, and intelligent systems. From the theoretical underpinnings to the practical breakthroughs, this session promises to expand our imagination of what's possible when machine learning meets the quantum realm. So, without any further ado, let's extend our heartfelt gratitude and a virtual round of applause to welcome Dr. Elias Fernandez Combarro Alvarez, professor, researcher, and quantum visionary, as he leads us into today's guest lecture on quantum machine learning and applications. It's truly an honor to have you with us today, sir.
Hello, good afternoon, good evening. Thank you very much for the very, very nice introduction. And thank you, of course, to the organizers for this invitation to talk about my research in quantum machine learning. Okay, so I've prepared a few slides. So I'm now going to share my screen and hopefully you will be able to see. Okay, so let me try and make this full screen. Okay, this should be better now. And today I want to talk a little bit about what is machine learning when it meets quantum computing, and also some of the applications that we have been developing here at my research group at the University of Oviedo, together with people from researchers from CERN in Geneva, Switzerland, also with researchers from the University of Cambridge and the universities of ETH Zurich and EPFL in Lausanne. So first of all, I would like to clarify what I mean by quantum machine learning, because if you read the literature, you will find like different definitions of what people understands by quantum machine learning. So in my classification of quantum machine learning, you have two different axes depending on whether you use quantum or classical data, and whether you use a quantum or classical machine to process this data. So the only meaningful situation in which I talk about quantum machine learning is when we use a properly quantum device to analyze data, which is the region that I have highlighted in green on the right top corner of this diagram. And I will be talking about the situation in which we analyze classical data with quantum devices. Even in this restricted definition of what quantum machine learning is, you can find like different research directions in the literature. The first of which started about 10, maybe 12 years ago, maybe a little bit more, and involves the use of foundational quantum computing techniques, like, for instance, the quantum Fourier transform or amplitude amplification, which, as you know, is the technique that we use in Grover's algorithm, to accelerate, to speed up the training of classical models. Okay, so you have a list of different quantum versions of classical machine learning algorithms that you can accelerate with the use of quantum techniques. Okay. The problem with this approach is that it usually needs quantum fault tolerance. You need quantum computers that can implement quantum error correction in order to implement and run these algorithms. And as you know, nowadays we are still far away from being able to run algorithms, quantum algorithms that require fault tolerant quantum computing. We are now approaching the era in which we can start to create a few logical qubits from physical qubits and implement quantum error correction to maintain, to keep the coherence of these states. But we are still not there, okay? Even with the kind of machine that we have today, which, as you know, has been called the noisy intermediate scale quantum device, okay, a device that is not very big and it still has some problems with the implementation of gates. The gates are noisy, measurements are also noisy, and you have interference from the environment. Even with this kind of device, we can try and solve practical problems to see if we can get some kind of advantage from using these machines. I'm sure that you all heard about yesterday's news published by Google's research team, in which they have shown that for a practical problem in the study of certain molecules, they have been able to apply current quantum computers to solve a practical problem. So this is the kind of algorithm I'm interested in, but not in quantum chemistry, but in machine learning. Okay? And why would we like to do that? Why would we be interested in applying quantum computing to learn from data? Well, of course, the first motivation is that we have these new devices, these new quantum computers, and we want to know what are the applications. What are the applications in particular in data science, in the analysis of big collections of data. But also we have this possibility of using the kind of quantum circuit that we can run today to create new algorithms, new models that maybe can obtain some advantage over what is possible with just classical computing. So the main tool that we use in quantum machine learning in this NISQ era is what we call the variational circuit. So variational circuits are regular quantum circuits in which we have some rotation gates with some free parameters that we use for mainly two different operations. For instance, in this quantum circuit here in my slide, The first layer of rotation gates, which are energy physics as accelerators, particle accelerators. This is important because in order to use quantum machine learning effectively, we need to overcome different challenges. Of course, you all know about the problems with hardware size, the problems with noise, the problems with limited access to hardware computers, to quantum computers, because, well, they are few and far between. There are not so many quantum computers nowadays available. But to me, from an algorithmic point of view, what is interesting is to develop new architectures that can better solve different problems in machine learning. Okay, this is something that the community is actively researching nowadays, but we don't have still all the knowledge and all the theory that we have in classical machine learning. In classical machine learning, for instance, you have convolutional neural networks, LSTMs, transformers, a number of different machine learning architectures that are very, very good at solving particular problems. For instance, convolutional neural networks are very good when dealing with images, or transformers are very good when dealing with textual data. Okay, so we would like to develop this kind of architecture for the particular case in which we use quantum neural networks. So the first problem in which we have tried to apply this is a problem in the classification of collision events in the LHC, the Large Hadron Collider at CERN in Geneva. Okay, so what you see here is what is called a Feynman diagram of a collision of, in this case, two gluons. And these two gluons, when they collide, they might create a Higgs boson. The Higgs boson is here depicted in red, but it can also be the case that instead of the Higgs boson, another gluon is created. So this is something that is completely random. Okay, you know that in quantum physics, events are probabilistic. You cannot control whether the Higgs boson will be produced or not, even with the same setting of your experiment. So at CERN, researchers want to collect data from those situations, those collisions
in which the
Higgs boson was produced.
So we want to
So we want
separate
to separate
those
cases in which we have a Higgs boson from those cases in which we only have a gluon. Okay?
The
The problem with this classification is that the Higgs boson and the gluon are very short-lived particles. You cannot observe them directly. They decay into other particles, and you only observe the result of those particles. Okay, so in both the Higgs case and the gluon case, you obtain exactly the same types of particles. So this is not something that you can use to differentiate between one and the other, to distinguish one case from the other. But these particles may have different momenta, different directions, different angles, and this is what we can use to classify these events into producing a Higgs boson or not. Okay, this is a problem that at CERN has been approached for many years with classical neural networks and with boosted decision trees. Okay, and they obtain some good results with these methods, but they require a lot of data. They require millions and millions of events. Okay, so we would like to try with quantum neural networks to see if we can achieve similar results, but with fewer data. Okay, in order to do this, we need first to reduce, of course, the training data set, but we also need to reduce the number of variables that we use, because as you see in the slide, we have 67 variables, okay? And we need to use 1 qubit to input each of these variables. So we cannot classify this, or when we started doing this, the biggest quantum computer was like 15 qubits or something like that. So this was something that we could not do. So the first thing that we did was to reduce the size of the data set, both in number of instances and in number of attributes. And we applied different techniques, okay? So autoencoders, some techniques that are called data re-uploading to reuse qubits to encode more data, and so on. And with these techniques, we use quantum support vector machines, which are one of the most popular models of quantum machine learning, and also quantum neural networks or variational quantum classifiers. And what we obtained was somehow below what is possible with deep neural networks, but it was similar to other classical machine learning models like random forest or logistic regression, things like that, okay? So we wanted to go a little bit farther and try to see if we could match the performance of deep neural networks. And what we tried was to define a new architecture in which this reduction of the dimensionality of the data was not independent from the training. So what we decided to do was to create a hybrid quantum classical neural network in which the first part is a classical neural network, and then we have a quantum circuit, a variational quantum circuit that performs the classification. So the first part, these blue circles here, are classical neurons that reduce the dimension of the input data. And then here we have our quantum circuit, and we train both together. And with this technique, we were able to almost match the performance of deep neural networks, but only with, let me see if I can point at this, only with 2,000 instances instead of millions of instances, okay? So this was one of our first research projects in quantum machine learning. If you want to know more about our results, I invite you to check this paper in which we describe all the experiments and the models and all that. Another interesting project that we've been involved with, together with people from Cambridge, the University of Cambridge and EPFL at Lausanne and CERN, is in the use of quantum versions of generative adversarial networks. Generative adversarial networks are not so popular today as they were a few years ago, because now we have diffusion models to create images very, very rapidly and with very good performance. But a few years ago, this was one of the main techniques to create new data, for instance, new images from a collection of data when you try to learn how to produce new examples, new instances following the same distribution. I don't know if you are familiar with the architecture of generative adversarial networks, but in these networks, we have a generator here in red and a discriminator in blue. These are, in the classical case, these are just neural networks, classical neural networks, and you train the generator to try to fool the discriminator. The discriminator needs to distinguish between real images and images generated by the generator, okay? And we train both alternatively, one epoch of the generator, then one epoch of the discriminator, until they reach a point in which the discriminator can no longer distinguish what are the real images and what are the generated images. Okay, with this you can learn, you can create images of people, for instance, that are something that had been used in the classical case at CERN to generate data from or similar to the kind of images that you get in the calorimeter detectors at the LHC, at the particle accelerator. Okay, as you know, running experiments in the LHC is very costly, so you cannot do it all the time. So you want methods that can generate data that are similar to the ones that you will obtain from the experiment, to calibrate your algorithms and to develop new theories and to learn patterns and things like that. So this was something that was done with classical GANs at CERN, and then inspired by different algorithms in the literature in which different versions of quantum generative adversarial networks were introduced, we tried to generate new images, but now with quantum neural networks, with a version of quantum generative adversarial networks. This kind of result was obtained before I joined the team in 2020 and was quite successful to generate images similar to real ones, but only when you have exactly one image. Okay, so you were always generating the same image. And this was directly inspired by these seminal papers in which you learn just one distribution. So the next challenge was to generate different images, to learn to generate different images, but all of them following the real distribution. Okay, so what we did in this case was to introduce a new architecture that we call the dual PQC model, the dual parameterized quantum circuit GAN model, in which instead of having just one quantum generator, in these articles, typically they substitute the generator from a classical network to a quantum network. What we did was to substitute this quantum generator with two different, so to say, quantum generators working in tandem. Okay, so with this, we were able to measure the results of the first circuit and then feed these results into the quantum circuit, and this quantum circuit will generate different images. Okay, and we keep the classical discriminator. These models are very, very difficult to train because even in the classical case, training generative adversarial networks is very difficult. So we had to perform a number of reductions, and we had to reduce the images to only 2 by 2 pixels. Okay, so in total 4 pixels, which are very, very small images, but we were able to train these models both with simulators and with actual quantum computers. Okay, and the results that we obtain, if you know about generative adversarial networks, for instance, if you see the image in the top, in the middle of the top row, you will see that we reach this equilibrium between the generator and the discriminator. Okay, so even if this is just a toy model, we were able to show that this can successfully train a generator that can then be used to generate new data. Okay, again, I invite you to check all the details in this paper if you are interested, and I will also I would also like to show you or to tell you about my favorite project in our collaboration with CERN, which has to do with quantum reinforcement learning. So in classical reinforcement learning, you have an environment, okay, that you want to control or in which you want to solve some kind of task, and you have an agent. And then the agent can observe the environment and get information about the state of the environment. And then the agent needs to take actions in order to solve a problem. For instance, one situation in which you have this kind of environment agent interaction is when you have a robot that needs to navigate through a maze, for instance. So the robot observes its environment and decides to move to the left or to the right or go straight away, and needs to find the exit of the maze. Okay, and that is the goal of the task. So in this kind of situation, you want the agent to be able to solve the tasks even in situations that have not been shown to the agent before. So you want to learn a policy that lets you to decide what are the best actions given the state of the environment. Okay, a situation at CERN in which we can apply this kind of technique is when we have the beams in the accelerator, the particle beams in the accelerator. As you know, the accelerator is a big circular tour that has a radius of 27 kilometers. So it's a very, very big accelerator. And you need to steer the particles to go all around the circle, all around the accelerator. And then you have two different beams going in different directions. And at certain points, they collide. Okay? And then you collect all the data for instance, for classification of events or with the calorimeters that I showed before. Okay? So one crucial task is to correctly steer the particles so they only collide at the points in which you are expecting them to collide and to collect it. Okay? You do this with magnets that deflect the particles, and they steer the particles all along the accelerator. Okay? So the first situation in which we try to use quantum techniques to learn these policies on how to deflect, how to steer, how to apply the magnetic fields to steer the particles was a very simple one that I'm showing in this slide, in which we had just one magnet and we want to steer the particles to the target. And depending on how well we align the particles with the target, we obtain a bigger or smaller reward. Okay? This kind of situation, this kind of problem can be solved with classical neural networks, in which you encode the state, which is the angle at which you find the particle beam in your detector. You encode this state and you feed this to a classical neural network, and then you are expecting to learn what is the expected reward of moving up, which will be the first number, or moving down the particle beam. Okay, so you interact with the beam, you interact with the magnet, and you learn which options go lead you to better rewards or to worse rewards. Okay, so this is a classical technique. What we did, following some proposals for much simpler problems in the literature, was to substitute this with a quantum Boltzmann machine, which is similar to a quantum neural network, but it's easier to train, for instance, on quantum annealers. Okay, so what we do is we encode the state and the action, and then we estimate the reward that we are expecting to see from this action in this state by the free energy of this quantum Boltzmann machine. And when we did this, we obtained spectacular results, spectacular results. So we trained this in two different ways, with what is called experience replay and without experience replay. Experience replay is that instead of interacting with the environment again and again and again, you interact just a few times, but then you make your agent learn from this experience several times. You repeat, you replay this experience, okay? So on the left-hand side figure, we see the results when we have no experience replay. And then blue is the quantum Boltzmann machine, red is a classical neural network. We obtain 100% optimality. This is, we solve the problem 100% of the times with just over 100 iterations, okay? Whereas with the classical neural network, we need over 10,000. So this is much more than we need in the quantum case. Even when we introduce experience replay, the quantum machine is faster. It trains with fewer steps than the classical neural network. Okay, and if we compare the sizes of the different networks, the number of parameters that we have in the quantum case is much smaller than the number of parameters that you need in the classical case. Okay, so this was very, very satisfying, but it was a very simple problem. So after this, we tackled a much more difficult problem in which we have many more magnets and many more actuators and many more detectors. So if I recall correctly, we have like 16 different points at which we can deflect the beam, and it's a much more difficult problem. And again, we try to solve this with quantum Boltzmann machines. The problem is that now we cannot encode the action just as move the beam up or move it down. We need a continuous variable. And in order to introduce continuous variables here, what we did was to take inspiration from the classical literature, in which you have what is called the actor-critic architecture, that works in a similar way to the generative adversarial networks. So you have an actor that is the one that proposes the actions, and a critic that learns what is the reward of that action. If you take a closer look, you will see that this structure of the critic is very similar to the structure of our quantum Boltzmann machine. So it was quite straightforward to replace the critic with a quantum Boltzmann machine and train a classical neural network with the help of a quantum critic. This is also very convenient in practice, because in the deployment of this model, then you don't need a quantum computer. You only need a quantum computer to train the model, to use this quantum critic. But then once that you have trained the classical network, you can use it in a classical machine. And in fact, this is something that we have tried in real time at the LHC accelerator, okay, and it was successful. In fact, our results were not so spectacular as the ones in the one-dimensional case, but we still obtain an advantage of about 30% reduction in the number of training steps. So from about 70 in the classical case to around 50 in the quantum case. Okay, so, well, this was kind of satisfactory, and it shows that, well, maybe for reinforcement learning tasks, quantum computers can help in reducing the training time. All of these results are collected in this recent paper. It was published last year. And if you are interested, of course, I invite you to take a look. And finally, I would like to mention that in addition to my research in quantum computing, I am very, very involved in quantum computing education. I think it's a crucial task nowadays because, well, we need more people who know about quantum computing and are able to apply quantum techniques in different domains. So together with my colleague, Samuel González Castillo, who was also one of the researchers in the event classification problem that I mentioned in the first place, I have published 2 different books. In 2023, A Practical Guide to Quantum Machine Learning and Quantum Optimization. And recently, just a couple of months ago, A Practical Guide to Quantum Computing. These are books that are targeted to people who want to learn how to use quantum computing practically. So we have, of course, all the mathematical background that you need in order to understand what you are doing when you are working with a quantum computer, but also a lot of code and practical code that you can run on quantum computers and on simulators to learn to program these algorithms. In the first one, we focus on NISQ algorithms, so quantum neural networks, quantum support vector machines, quantum optimization, whereas in the new one, we focus on algorithms like Grover's algorithm or Shor's algorithm, okay? So, well, we kind of cover both directions in the quantum computing algorithms in these books. And, well, that's all I wanted to tell you about. Thank you very much for your attention. And if you have questions, I will be very happy to try and answer them. So thank you very much. I don't know if you are asking any questions because I think you are muted, so I cannot hear you. I'm sorry, I cannot hear you. I think you are muted.
Sir, am I audible?
Yeah, now I can hear you.
Sir, as you said, it is trained and work properly in the one-dimensional data. My question is, does it shown results in a good way when it is given 2D and 3D data also?
Sorry, I could not hear the last part of the question. May you repeat it again, please?
Sir, as you said, the quantum bolt-on machine is trained with 1D data. What's my question is, does it work properly on 2D and 3D data too?
Yeah, well, I mean, this extension that we did with the actor-critic architecture is what allows us to work in higher dimensions. Okay, so the first model only works with one dimension, but then we extended this, and we, in principle, if we have big quantum computers or quantum computers that are big enough, we can work with any dimension.
Thank you, sir.
My pleasure.
Seems like that's all with the question and answer session. And thank you so much, sir. Thank you so much to Dr. Elias Fernandez Combarro Alvarez for the truly insightful and intellectual invigatory section, actually. You have taken us on a captivating journey throughout the NISC era, variational quantum machine learning, and the intricate challenges of quantum machine learning, illustrating concepts throughout the Higgs boson classification problem with its 67 variables and comparisons between BDTs, DNNs, and their quantum counterparts. Your discussion on dimensionality reduction, QSVMs, and VQCs, and also the hybrid architectures showcased how classical and quantum paradigms can beautifully converge. The explanation of GANs from their classical form in high energy physics to quantum GANs and the dual PQC model, along with insights into quantum reinforcement learning, QNets, and quantum Boltzmann machines was truly an eye-opening thing to hear. And on behalf of all the RGUKT Srikakulam University and the Qiskit Fall Fest 2025 team, I extend our heartfelt gratitude for sharing your expertise, your clarity, and your passion. Sir, it's been an absolute honor having you with us today. And thank you once again for inspiring us to think beyond the classical and venture into the quantum field. Everyone, let's give a warm virtual round of applause for Dr. Elias Fernandez Combarro Alvarez.
Thank you very much. My pleasure. Thank you.